There we go. What's up, y'all? We're doing a little overtime today. We're doing day 4.5. Let's get the vibe check real quick. Honestly, right now, I'm just feeling lucky. Because if you live in the Midwest or the East Coast right now, you are covered in smoke from fires. From fires in Canada, where we question fire management. We question whose fault is this? Is this really climate change? Or is this negligence that causes you to be inside in the summer? You only have so few nice weekends in the summer in the Midwest. So this is forcing you inside on these precious days. When I lived in Seattle back in 2018, same thing happened. Perfect time of summer. Forest fires. Where were the forest fires? I'll give you one guess. Canada, of course. British Columbia. We gotta get these forest fires under control. We have all the power to do it. We need to do it. We need to save the forest. All right, let's get into what we'll be working on today. So, in this stream right here, what we're going to be doing is we're going to be leak coding because I have to do we're going to be doing like an hour a day of this stuff. So, let's crank out an hour first, and then we'll do some reactions, some vibes after. And what we're going to pick up is one I wanted to work on. It's a binary sort. It's a binary search. Which number is it? First and last. All right. We are going to reset this and try to work on it again. So, as you saw, this is one I've worked on before. But we're going to work on this one again. We're going to go ahead and try to solve this. So let's go ahead and open up. Let's go ahead and open up our IDE. Perfect. Let's get our IDE up. This seems crazy big. There we go. That looks a lot better. Look at this, by the way. This is when I was running trigraphs. See if you could read this code. See, like if I showed you this and told you this is valid C++, you'd be like, what? This is valid C++. See if I still have the sticky up for the conversion. I do. So, these 3 character sequences represent single characters to allow for keyboards where you didn't have these. So back in the day, IBM, ruled everything with the keyboards. And they didn't have for their keyboards a lot of these characters. For example, hashtag, curly braces, square brackets. All these things were just not included. So this is how you represent them right here. Let's go ahead and create another file real quick. We'll call it all right. We'll take this and we'll just and then this just compiles it. We could turn off the trigraph flag. We can change this to bsearch. We'll go bsearch. for the output file. Okay. Let's get ahead and let's start adding all the things that we need. Oh, let's so I have my settings JSON in, and look at these statuses. This is what you have to disable to enable trigraphs. So we're gonna go ahead and comment that out. And we might need to. Okay, now let's open back up eSearch. Give me a sec to figure out what to do here. I might need to close it, open it back up. Let's try that. Huh. Honestly, I might delete the file and try it again, as you saw in these. All right. All right. Okay. Let's go get that font. Let's go get it. All right, let me grab the inputs right here just so I can see the inputs. Okay. The goal today is this. We're not going to be doing a full test-like setting, but we're just going to be working through problems, just repping problems we've done in the past to build them into memory, build in this data structure to use into memory here. So what we're going to do is solve this, and let's go ahead and read this prompt here. So given an array of integers, num, sorted in non-decreasing order, find the starting and ending positions of a given target value. So we're given a target value, and we're given an array of ints. And what we want to do is we want to look at each one, and what we want to find is the first and last occurrence index. So for example, in the first example, it's 8. The occurrences are 3 and 4. So we're going to find the first and the last occurrence of each element in the sorted array. So let's talk about this. What do we know? Well, right off the bat, what we know is that the list is sorted. That's the biggest tell here. You hear list is sorted. What does that lead you to do? Oh, the optimal solution is log n. Immediately, that's what you first uncover about something like this. So whenever you hear sorted, it's always going to be a log n solution that they're going to most likely want you to do, unless it's a completely different problem. But it pretty much sorted. Either think it's you're going to use the index, like a bucket sort, where maybe you would use the index for something, maybe finding duplicates you could do. But mostly when it's sorted, 90+% of the time, log n. Get log n out. So we know log n is just a binary search. But what we're missing here is we're missing how do we get the first and how do we get the second index? Because again, binary search is only going to give us one. It's only going to give us one index in this. So how could we solve this even better? Well, let's go ahead and walk through it here. So now that we know all that, how do we get through this? So we know we needed to use binary search. And let's say above, let's just go off this example here. And let me make sure this is large enough. That's probably better. Let's go off this example right here. It's too large. I think it's fine. We'll make it a little bit bigger. All right, so let's get into solving this. So we know we need to run binary search here. So right off the back, I already know that we're going to have to hold on to another function for B search. So we could pass in the vector int reference to nums. Okay, so we have this here, and we know this is where we want to run it. We want to pass in all this, but we're going to want to pass in more than just all this, because what we're going to find out is we're essentially going to have to use bsearch here to find the first and the last. It's essentially what we have to do here. So finding the first and last, that's 2 searches. So we need to run this twice. And when we run it twice, whenever we find it, so we find our target, all I need to know after we find our target is you keep going to the left. So once you find out, oh, it's our target, all we have to do is binary search to the left. And then for the other one, binary search to the right. So what do I need to know? I need to know if I'm looking for the left or the right here. So let's go ahead and let's add that in here, which will just be a Boolean of left search, we'll call it. Okay, so let's now get into calling this here. So we're going to call... So one thing I forgot to mention is this is what it looks like right here for the output. So we're turning it in an array, and it could also be an array of -1s. So how do we do this here? What are we going to do? So we're going to just hold on to each one. So we'll go ahead and int left equals bsearch nums target true, and then equals bsearch nums target false. Okay. So change the return type there to an int. Perfect. Now we're going to go ahead and solve bsearch here. So what do we do here? We need to hold on to the indexes. So we're going to go ahead and do int left equals 0, int right equals nums.length minus, or nums.size, excuse me, -1, and then we need to get the middle. So the middle here, how we get the middle is you go like this: L plus R minus L divided by 2. Okay. Now that we have left, right, middle, now we want to run a loop here. So it'll be if L is less than R. So while the left pointer here is less than R, what are we going to do here? Well, what we're going to do here is we're just going to keep updating the left and right pointers. And so what we want to do first is we want to move the middle in here. And then after we move the middle in here, next what we want to do is we want to go left and right. So let's go ahead and do that. So let's first get in current number equals nums middle. Let's spell this right. Okay. So if current number, so we found it. We found it right here. And then we have to add less than or greater than. So we'll do that right here. Current number. So if current number is greater than target, we want to move L to the middle. If current number is less than target, we want to move right to the middle. I think it's actually, we should probably do middle plus 1, I believe. Now, one other thing to note here is this has to be actually like this. Let's go ahead and make it actually run with gated logic here. All right, so we'll make that run with gated logic right there. And then this is the else block, because we don't want anything to hit any of these gates after it's hit another gate, since all we're doing is changing the left and right there. So this is the big part of the algorithm right here. So what we're going to do is we're going to define res here to be -1, okay? So we're going to define a res here to be -1, and then what we're going to do at the very end is we're going to return res. So we're going to return res there. We'll return res there, and then we'll change it. So if it's not found, we return -1. If it is found, we return the number. So now into the meat and potatoes of this algorithm here, because what we're doing is we're just finding it, okay? So we keep chopping. We literally chop it in half, move left or right, and then get a new middle from the new numbers, and then keep going. That's currently what we're doing. So what do we need to do now? Again, like I've alluded to earlier, is we need to know if it's search left. So first thing we need to do is do if left search. Okay, so if I'm searching to the left, what do I want to do? Well, we need to hold a temporary here too. And this is actually going to be res. So all this has to be is res equals current number. But it's actually the index we're looking for. So it would be middle. Yeah, middle would be what the index would be. Interesting. Okay. All right, so if it's left search, what do we do here? Well, we set right equal to middle plus 1. So this way we just keep searching, we keep shrinking it to the right. So by doing this, anything we find, so if we hit this else block again, we switch res, because we know, okay, we found another number that's a less index here. Now I'll get into more of this, but it's a good thing to understand here. Why do this? Because since we know it's sorted, we could just, once we use binary search to find the number, and I want to see if it's less than, I could just look at every position left of it. Or just until I get a different number. Because what we know is it's in sorted order. But what you have to think here is that could easily lead to an n level time complexity here. Because what if every element is your target element? Then wherever you find what you're looking for, you would look all the way to the end of the array. That's where, I mean, log n is so efficient here because 10,000, let's say you had a list of 10,000 items and you want to run n level time complexity on that. Well, worst case, you're doing 10,000 searches. If you're doing log n with base 2, because all the computers use this in base 2 in computer science, you're essentially halving it every single time. And so real quickly, you realize that you only perform 13 operations at most using log n compared to 10,000 as the worst case. So that's why, even though a lot of the time with inputs, you doing this would maybe be a little bit of extra work because we already found out we just need to look one index to the left of it. But when you look at the base case and other things, it's really not. So let's get in and solve this here. So left search, do that. Right, do this. And that is it. And now we just return. So easy to implement this. This is a little difficult, like intuitively, to just think to do that, because what you'll think is like, oh, I use binary search to find it, and then I'll just look to the left. Like that's what a lot of people would think to solve, would be doing that right there. But really, it's you keep going another logarithm down, cutting the input, slicing the input. Perfect. All right, let's go ahead and put this in, see what I misspelled, and we'll go from there. Jeez, I think the whole thing is kind of messed up. Did it get everything? No, it didn't get everything. There we go. Okay. Let's go ahead and run it. Let's start seeing what's going on here. Will this run first try? No, absolutely not. God damn it. What did I do wrong? So time limit exceed, that means it's never... It's never finishing. Let's see why. Is it because I'm missing that last case there? Because it'll probably keep hitting found. All right, let's see. Mm-mm. So the correct logic, I'm literally just missing one thing here because we are moving through this correctly. This might be wrong. This was like in binary search, was a long bug in binary search when we had things that were too large. But what we could just do is L plus R divided by 2. So we could do that. That might be why is the middle picking is wrong. It probably is. No, it's not, huh? We'll take a look. We'll give it a minute, and then if not, we'll get some assistance to see what I did wrong. But let's see if I can find it. Am I even returning? I'm not even returning it. I'm returning res from here. It's because it's getting stuck in this while loop. Why are you getting stuck in the while loop? This makes sense because this would not fire correctly. All right, let's take a look. And see, this is what I hate. Feel like I know it. It's like translating it to C++ has just been freaking hard, and it's been really biting me. But I'm not going back. Not a chance. Oh, shoot. Oh my god. Jesus Christ. Cheese and rice. So dumb. I knew I was going to get that logic wrong. Alright, so if you didn't see what I did wrong, is I'm increasing the middle when I should be moving it to the left one instead of to the right one. So we want L to go to the right one, and we want R to go to the left one. So let's go ahead and implement that there. Let's go ahead and implement that there. Perfect. Perfect. All right, let's take a look. What else did I miss? Yeah. This is literally what I have. This is literally the exact same thing I have. What the hell changed? God, I just have all these confused, don't I? R equals middle minus 1. Good lord. Is this a Pokemon trap beat? This is insane. Then obviously this is L plus 1. Alright. I don't see, for some reason, that logic there is so simple. Like, I know the approach, I know everything, and then it's like I start blanking for no reason right there. Where it's literally just, oh, you had literally the exact right idea. You just did not shrink everything correctly. You just thought of the logic in reverse, which, I mean, it sucks. I mean, it's cloudy in Atlanta, but we're going to have to get it so we could see this every time, because it comes to me how to solve it fast. It doesn't come to me the translation now. Because we're using C++, because we're not using JavaScript for LeetCode anymore. Not a chance. All right, let's move on to another one. Let's do a graphing one. This Pokemon mix is insane. I don't think I've ever heard a better song for LeetCoding. In a world we must defend. And I'll teach you. In honor of Canada. In honor in Canada with the forest fires, we will be doing number of provinces. Can I name all 13 provinces in Canada? Yes. Let's name them all real quick. We'll start west in movies. So we got British Columbia. We got Alberta. We got Saskatchewan. We got Manitoba. We got Ontario. We got Quebec. We got Labrador, Newfoundland. We got Nova Scotia. We got New Brunswick. We got Prince Edward Island. And now the 3 territories. We got Northwest Territory, Yukon Territory, and my favorite, none of it. How much of that land is livable, you may ask? None of it. That's why it's in the name. None of it. All right, let's get to this. So these always there's a lot of typing whenever you do these. So let's get after it. There are N cities. Some of them are connected while some are not. If city A is connected directly with city B and city B is connected directly with city C, then city A is connected indirectly with C. Yeah. A province is a group of directly or indirectly connected cities. Okay. And no other cities outside the group. Okay. Okay, so I got my Saskatoon, Saskatchewan right here. All right, so you are given an n by x matrix is connected. Of the I city of the J city. If the I city and the J city are directly connected and is connected, IJ equals 0 otherwise. Okay. You're given a matrix is connected. Okay. Okay. How does the matrix translate the flights? Where is connected IJ equals 1 if the I city and the J cities are directly connected. All right. So they're not giving me something to traverse through here. I'm getting a code to know if they're connected or not. So you're given an n by x matrix where is connected IJ. So literally, if it was 0 and 1, which is 1 here, if the I city and the J cities are directly connected. So it's 1 if they're directly connected and 0 otherwise. Okay, there we go. Now we're talking here. So let's go ahead and take some notes, some pseudocode here, notes here, just so I can make sure we're traversing this right. So if I J equals 1, cities are directly connected. If I J equals 0, cities are not connected. Okay. Return the total number of provinces. So, what are the rules here for returning provinces? 4 provinces. We keep going until we get to zeros. Let me read this one more time. Okay, so I'm just finding in this the number of ones. See, this is what I'm just trying to understand. Is it just me iterating through all these arrays, or does this have anything to do with something else? I don't think it does. A group of directly or indirectly connected cities and other cities outside of the group. And no other cities outside the group. Okay, so that's a key piece right there. No other cities outside the group. So, for example, they can't be connected, these three right here. Okay. I think this is easier than I think. So it's literally saying a province is just one. There's no disconnection there between provinces. So all we have to do is a group you were given M by X matrix. Okay. We have to generate the matrix. Okay, so this is our matrix. Okay, now I'm finding I'm thinking of this right. So it's going to be a matrix. Let's go ahead and draw it out. Let's see if this works. Okay. Okay. Too big. Okay, so this is what it looks like. Let's just say it's 3 by 3. Good lord. There we go. Okay, so let's say it's 3 by 3, and it's like this. Okay, so this is what we're getting back. Provinces are group directly or indirectly connected cities. Directly or indirectly. I literally just don't understand the question here. Like, what exactly is a province? Let's get a nudge here on what to solve for this. I literally can't even think of what they're trying to ask me to do. What is needed for this elite problem? Yeah. So, okay, but that's just tell me what a province is. Like, I still don't understand what defines. So a group of states that are all connected to each other directly or indirectly. Okay. This is what I need right here. What is this referring to? How are these connected? So stupid. Tell me how these are connected. Okay. All right, this is what I don't understand. Oh. Search done. Yeah, my brain's pretty cooked right now. All right, let's walk through this. All right, what is J though? Like, this problem explains so bad. Dude, this thing is explained terribly. I can't even believe this. All right, so we're going to iterate through each group. What we're going to do is we're going to pass in each row in. So we're going to pass in each row and the size of the array. So first thing we do is loop through the array. So we loop through the array. And then... All right, but this is the part here on line 30. City J equals 1. This is just what I'm trying to wrap my mind around. So, like, is each row connected? So we see if the city equals 1. And then where do we go from that? This is weird because what it looks like we're doing is we're just on that same row. Because we're not changing I at all. And we passed in I as city right here. Okay, I see what we're doing here. All right, the wording of this is trippy, but the concept is pretty similar. So what we do here is we start... So the wording that mostly tripped me up about this one is how to tell if something was connected. Because usually, like if I'm going to a coordinate, like you would think of like an adjacency list, like you would know where that cell would be connected to. And to me, that's mostly how I've done these problems is, you know, you see a cell and you know it's connected to another cell. And so you could just follow the DFS, could either go up, down, left, right on a board, or wherever the cell is tells you where to go next. But here is different. What's happening here is we're essentially going through. So we start at index 0. We're going to start at index 0. And we say, okay, it's index 0 is row 0, column 0, 1. If it's 1, guess what? We keep looking. If it's 1, we keep looking. If it's 0, we just return. At most from here, from this call, we could return 1 province. Because the other provinces would be caught by it keep going through I. So let's go ahead and type this code in. We'll walk through it. Sorry guys, getting a voicemail. Hey. One second, guys. Client. 4 p.m. Client meetings. All right. So we're going to walk and talk through how to do this. Because just even understanding what this problem meant to do was stupid. They didn't do a good job of explaining it. At least I don't think they did. So what they're basically saying is, okay, each one per each group is a province. And if two ones are connected, then the province continues. So essentially all we're doing is the following. We start at each one and we go from there to see if it's connected. And we know not to go back to ones we've seen because of a visited array. And all we do is check on this same level. We check on this level, we check on this level, and we keep going through. So let's go ahead and let's get this down here. So first thing we want to do is create our visited. So it's not a two-dimensional, and this is why it's so trippy, because I'm so used to this being two-dimensional. Two-dimensional, you're either going up, down, left, right, or diagonal, or it's like an adjacency list. This is trippy because it's so simple. It's so simple, which makes it difficult, which makes it stand out, honestly. So we're going to create a visited vector here. It will be of is connected dot size. I don't think you need to put in that last thing, because it'll just take false. So take the default value as false. So we got visited here. Next, what we want to do is have the counter for provenance. So as we know, each time we're scanning from left or right, essentially here, we just need something to aggregate every time we find it. And at most, we could find one as we go through. So let's go ahead and put in. Okay, so for int I equals 0, I is less than. So let's change this to size t. So let's change it to size t, and let's do is connected dot size. Okay. So we're going to go through each one of these. So we're going to have this group first. And what do we want to do with this group first? Well, first, we want to make sure that where we're currently at is not visited. So how do we do that? How do we know if this is not visited? Interesting. So the last thing about this, I just need to understand right here. So visited J. So visited I. So the city is I. Okay, so we put in 0 as. See, this stupid two-dimensional stuff about this is such a bad way to explain what to do here. Like, just tell me, okay, do I have to go left and right? And if it connects and doesn't connect, is that a province and I increment the counter? Like, it's that simple to say. So, but I just want to know why visited J is the same as visited I. Is I and J a city? I think every I and every J is a city, but let's see how I would explain that. All right, and this is why it's confusing. If the ith city and the jth city, okay? Now, what does that mean, ith and j? So what that means is the rows, each row, so in here, 0, 1, 2, 3 are 3 cities. And then in each column, this is where you see if they're connected or not. So I and J are 2 cities. So rows and columns are 2 cities. That's the most confusing part of this whole thing, is understanding that those are cities. All right, so let's get back into going into how to do this now. So now that we know that those are both cities, all we have to do is mark them off using the same index, because the same index will be able to know. And you could know why I used size up above on line 4. That's because we know that we can only visit everything within our group. We can't visit more than that. So that's how we know what to use here. We could reuse. So if it's not visited, and DFS is connected, yeah, the visited, and then we could pass in I, and we could pass in is connected. Dot size. Okay, this is perfect. And then all we do after this is return provinces. Okay, now let's create another one, and we will vector int Okay, so that leads us to this right here. So what do we do here? Well, we have a way to, we have a reference to our visited here. So first thing we want to do is mark this as visited. So all I have to do is go in here. Okay, so we marked it as visited. So again, like this logic is tough. If I is 0 and J is 0, then the cities are not connected. So their two cities are connected. That's how you go through it. So if they're connected on the same number, because it's an M by M graph, that's how you know here. All right, so let's go ahead and get through this here. IJ. So if it is connected and it's not in visited, then all we do is DFS again. Okay. So void, it's going to not return anything, but we don't need anything. All we needed to do is mark up our visited. And every time we run it, we know that's just one occurrence of it. What did I spell wrong here? I did. I did mean visited. Oh, duh. Jesus. So bad. There we go. Okay. So the hardest part about this one is understanding what they're actually telling you to do. This is literally what you do almost every single time. Every single time you create a DFS like this, where you're either looping through, and this is determined at the time looking at the problem, like, are you just calling it? Are you looping through? A lot of times if you're looking at a graph, you're not just looking at each row. Again, another thing that's trippy about this one is because you're just looking at the row. Most problems are you're going to have to be doing 4i, 4j, and then you're going to have to call DFS and pass in I and j for the current cell. That's normally how you would do things like this, but this has a little mix on it, which is interesting and gets you thinking a bit more. I don't like how this was laid out at all, but this type of functionality here is literally all you need to know to be able to do these. Just know whatever problem they say. The minute you identify it as a graphing problem, you build this for DFS. And it's very rarely is it going to be BFS. It's almost always DFS. So make sure you build DFS. Like I guess if it's like reverse a binary tree, or yeah, that would be, or not reverse, shift diagonally or something where you rotate everything in the tree. That's when you could use breadth first search. So that's it here, y'all. We got them down. A decent amount of practice. We did an hour. I mean, it looks sloppy. It's going to be sloppy because we're working on them. And it's crazy because I spent like a month doing these recently. Like literally 2 months ago, I spent like a month. And lately, all I've been doing is talking with clients and building this project, which taking up so much of my time. And it's like I already lost what I gained. But the thing is, it's so easy to find it. You just have to get daily practice in. So the daily practice will be going on, and this is just going to get better and better to the point where we're crushing them. We'll have to learn more about C++, obviously, to make sure we can use the language more efficiently to do different things. But understanding how to do these, I almost always recognize them. I'm almost always able to do them. But we want to pass all of them. That's everyone's goal, is to pass all of them. So that's what we'll get to, is passing all of them. All right, before we go, I got some time. Let's take a break and let's have some fun. All right, let's have Claude build us a tier app. So we're going to have a tier app built, and then we'll go ahead and rate things. CD. Now let's give it. Okay, I want to create another tier list. This tier list is going to be comparing everything about Dallas versus Houston. So the comparables will just be a pro for Dallas and a pro for Houston. And what I want as a tiles is transportation, jobs, weather, city, infrastructure, airports, numerous things that could be used to scrutinize about the cities that go over which one's better. And we'll look at a rating here, include stuff for tech workers, because we want to also see which one would be better for tech workers, but make sure we have a lot of things to go over because we want to do an accurate comparison of these two cities. Okay, let's go ahead and build this. Let's vibe code this app out, and then we'll run through the actual comparison. So we're going to run through to see what is better for tech jobs. Is it Dallas or is it Houston? And we're going to look at a lot of different things here. But first, while we wait for this to build, so let's look at Houston. So Houston has unbelievable housing prices. I have really good friends that live in this area here in the Heights. Now, let me tell you, this neighborhood is a gem that's just not talked about enough. I love this neighborhood. This is where I would live if I lived in Houston. Their home there is cheap. It's like a 4-bedroom house for like $2,000 a month. Where else are you getting that? And where are you? No, you're right next to the city. And look how connected this area is. And with how much slack Houston gets, I mean, this is dense for Houston. It's a very nice, dense area. Now, let's see what's for sale. Look at this, 3,800 right here. Dang, has inflation been this crazy? He did get his place like 5 years ago. Wow. 3,800. All right, let's go check out another market here. Let's check out Dallas. So in Dallas, I'm obsessed with this area right here. This is where we lived. It's such a great place, close to Lower Greenville. Honestly, if you want to live in Dallas, this is you live here or you live in Uptown. Anywhere else is not good. Not good. You're kind of a tweener if you're anywhere else. One thing I really like about Lakewood is if you like nature, this is the only nature you're going to get in Dallas is White Rock Lake. It's the only thing. So if you don't live close to this lake, you're not going to have really anything to do outdoors. We spent a lot of time at this lake. This lake is phenomenal. It really is. I mean, it is a Texas lake. Keep that in mind. But let's look at these prices here. I mean, you're not going to find something here under $1 million, which is crazy. And this is where you want to be. So let's also move over to other places where people enjoy living. This area here, Knox Henderson, is really good. You could find a lot. I mean, this stuff here, it comes at the premium, and then obviously this gargantuan right here, Highland Park. I mean, look at the difference. This is in Highland Park. This one's $4 million. Damn. See, like this is overpriced as hell. So you're gonna get a townhome. You're gonna get a townhome? What? Oh my god. $4 million. This is your freaking backyard in Dallas? Are you kidding me? What the hell is going on? Alright, I mean, literally any new construction looks like this. I mean, it's big. It's 5,300 square feet, but that backyard's tiny. And most importantly, it is in Dallas. You spend all your money getting this $4 million house, you have to send your kids to Dallas ISD. Which, trust me, if you're buying this $4 million house, you're gonna want to send them to private school, or you want to be in Highland Park. So, what could you get in Highland Park? Oh my God, I'd buy this 10 out of 10 times over that one. Are you kidding me? This is basically the same price. Who is the housing market just destroyed now? My God. It's crazy. All right, let's get everything here. Tier list is coming up shortly. All right. All right. Y'all ready to get after this? Let's make it bigger. No, this is good. All right. Kind of cuts off a bit. Here we go. We'll make it like this just so you can see more of it. So let's start off here. Transit. See if we can make this screen a bit bigger. There we go. So let's go ahead and make it just a little bit smaller so you can see this part here. All right. So what we got up here is we have a scoreboard, Dallas versus Houston, and we're going to go over everything and rate who gets the better ranking. So we're actually have this built in a better way. So let's start off with transit. All right, this is pretty easy. The Dart wins, but overall, the Dart is like I honestly would put it in E tier, but I mean, it's functional. It could take you places, but it breaks down all the time. It gets a real big knock for me because just like the Houston Metro here, which goes squarely in E tier, and the only reason that's not an F tier is because it's not like broken down. Like, you can still operational to use it. So Dallas has the better transit options here. They have the largest amount of light rail in the country, but they literally have probably the worst ridership of anyone. I mean, how could this be? Well, it's simple. You build. Watch. Let's take a look at what it looks like surrounding these DART stations, and I'll show you why. Literally no one. DART station. All right. So let's go pick one. Let's go Forest Lane, okay? And let's see if we could pop this up to walking here, and let's go right here on Forest Lane. Yeah. So this is where you're gonna get dropped off with no car, nothing. Look at this. You're done for. You think there's anything to walk to here? If you get dropped off here, I mean, yeah, they have to have a unreal sized parking lot that'll never be full. But let's see, you can walk to this huge shopping center. And this is most stations are like this. I mean, oh, look, here we go. Finally, we could go to Choice Grocery and Checks Cash. Perfection. That's exactly where we want to go outside of the DART. 100%. That's where we want to go outside of the DART. So all these stations look like this. Oh my God. Fair Park Station. Give me some of this. So this is the only route I've ever really taken in Dallas. I don't even take it to the airport. You know why? Because it drops you off at one terminal. It could be in any terminal. Look at this. So you would go here to go to the Cotton Bowl in the State Fair. That's the only reason you would take this. You would never come here. So it's super useful during a very small time of year. And again, it's like, why is it not useful more than that? Because there's nothing here. I mean, there's buildings, but there's nothing in any of these. There's nothing going on. No one's doing anything here. So literally, this type of infrastructure where you don't put anything next to rail, yeah, no one's going to use rail if it doesn't take you anywhere. It's all about destinations. So let's go back here, and that's my spiel. Let's go to highway traffic. So highway traffic, they're both C's. If you live in any large city, they're C's. And I honestly might say Houston's a D. But I think that's too high. We're going to go DE again. Just thinking about it, it's better than extremely large cities like obviously Los Angeles, obviously Boston, obviously New York, obviously Chicago. But they're still horrific. And it's like, it's your only way to get around. So you're not going to enjoy any of that. Airports. All right. Dallas, A. IH, Houston. So it's DFW and Dallas. I want to put it in S, but it's not S at all, and I'll go into why. And then Houston is C. It's United Hub. I'm very biased. I like Delta a lot. There's a good amount of Delta flights out of Dallas. And then I also like American Airlines a lot, too, which has a good hub. You have a good amount of destinations. It's obviously not Delta now, and being in ATL, you're very, very much like you fly Delta because this is the hub. But Midway and Love Field, they're almost unusable unless like you're some crazy person that does like Southwest or something. I mean, the only flight I ever took out of Love Field was a Delta flight to Atlanta. There's no like, you don't save money using Southwest. So unless like you're some person that uses Southwest, you'll never use Dallas Love Field, which is the better positioned airport. It's right next to Dallas. So you have this amazing airport right next to Dallas. And it's not accessible by most people. Most people have to drive all the way out to where is that? Grapevine, Texas to go to the airport. Crazy. All right, job market. We'll go A. We'll go A2. Depending on what industry you're in, the jobs here are phenomenal. You're going to find a lot of really good jobs that pay high. And, I mean, the cost of living is rising in Texas, but things are going down. All right, y'all. I got to let you go. I have to get ready for a client meeting at 4 p.m. It's great hanging out with y'all. We'll be on again to do more leak coding, more getting sharper, more making our skills better. Let's take care, guys. Bye.